So let's do some applications of derivatives now, and this goes hand in hand with this topic specifically, related rates. It goes hand in hand with implicit differentiation, which is why I'm doing a video on it right after implicit differentiation, because you don't forget how to do implicit differentiation after you get used to it. So let's jump right in. So related rates. Let's read this example from Paul's online math notes for Calculus 1. Air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So we're no longer dealing with functions with respect to x. We're dealing with functions with respect to time. And namely, the first question you should always ask is, what are the functions with respect to time? What are the functions of time? So air is being pumped into a spherical balloon. That indicates volume. So the volume of this balloon is changing with respect to time. So in other words, volume is a function of time. And how do we express that in math notation? Well, V is volume. V of t is how we would express that. V is a function of time. And what else is changing with respect to time? Well, if the volume is increasing, I would also garner that the radius of the balloon is increasing, because it's asking us to find the radius of the balloon when the diameter of the balloon is 20 centimeters, or in other words, the radius is 10 centimeters. So the radius is also a function of time. So we denote that with r of t, little r of t. So to calculate this, we need after you make these conclusions that volume is a function of time, radius is a function of time, now you need to ask yourself, what do we know and what do we need to find out? So we know volume, we know V of t, we know r of t, so let's write that down. Well, we don't know V of t, but we know V prime of t, right? We know the rate at which volume is increasing, which is 5. Well, it's centimeters cubed per minute, but we're not physicists here. We don't care about units. So V prime of t, we know r of t, so that's 10 centimeters. And we want to know r prime of t when r of t is 10 centimeters. And we accomplish this by plugging in r of t when we get there. So after you do this, after you write down what you know and what you don't, you have to find a relevant equation that you can differentiate with respect to time. And you might be thinking of the equation for the volume of a sphere, which, if I recall correctly, is 4/3 pi r cubed, right? So this has everything we want in it. It has v, r, some constants, it has a pi in there. So let's try applying the derivative operator d dt to both sides of this equation. So what do we get? So we get the derivative of v with respect to t, so we get dv dt is equal to 4/3 pi as a constant, so we can keep that out. And what is the derivative of r cubed with respect to time? So the derivative of r of t cubed. Well, we have to use the chain rule, where f is t cubed and g is r of t. So what is the derivative of t cubed with respect to t? That's 3t squared, but instead of t we have to put r, because we're replacing that t with r of t. So this is going to become 4/3 pi times 3r of t squared, but we're just going to put r for convenience, 3r squared, and we have to multiply by the derivative of g, which is r prime, or dr dt. That's how I'm going to write it. I'm going to use Leibniz notation here. So dv dt equals 4/3 pi times 3r squared times dr dt. Let's make that a little bit cleaner. So dv dt is equal to 4 pi times 9r squared over 3, so the 3's cancel out, dr dt. So that equals 12 pi r squared dr dt. So I'm going to erase this top here so I have more room to work with. Sorry. And so we have, let me just rewrite this so it's a bit more viewable. dv dt is equal to 12 pi r squared times dr dt. So what did we know? We knew that dv dt is 5, so let's plug that in. So 5 equals 12 pi, and what was r? Radius is 10 centimeters. So let's plug in 10 squared. And what's dr dt? Well, we don't know what dr dt is, so I'm going to write that in blue. And now everything here is a constant except dr dt. So all we need to do is solve for dr dt. So let's divide by 12 pi times 100. So 1200 pi is equal to dr dt. What is this equal to? 1 over 5 divided by 12, 120 is 24. So it's 1 over 240 pi. And this would be in, if we did our units correctly, this would be in centimeters per minute. So this is an application of implicit differentiation. We treat v as a function of t, we treat r as a function of t, and we use the chain rule if we need to accordingly solve for, a certain variable, whether that be r prime or v prime, whatever the formula calls for.